Hi and welcome back. So up to this point, we've identified what is a covalent bond and how to make these covalent bonds from Lewis dot structures. Today we're going to be looking at the actual shape, three-dimensional shape that these particular covalent structures take, and how to predict the shape simply based on the molecular structure. Okay, so let's start off talking about molecular shape with a problem, and I mean that in the sense that there is an issue with just relying on Lewis dots to kind of tell us what the molecular shape is going to be. So let's look at this, and the problem is let's draw a Lewis dot diagram, so as to say all of the dots that form the covalent bonds for methane. Methane is CH4. And so if we look at carbon right here, carbon, and this is an abbreviated periodic table. You can see we've kind of left out the main middle part here, the transition metals, because we're just interested now in non-metal bonding, so we're going to be focusing mostly on these kind of purplish structures. And we can see carbon is right here, and it should have 1, 2, 3, 4 valence electrons. So 1, 2, 3, 4. And then hydrogen, of course, is over here. Hydrogen has that single electron, that one electron. And so if we have CH4, then let's construct this. We have 1, 2, 3, 4. And if we were to kind of draw this in an appropriate Lewis dot structure, we would say something maybe like this. And carbon's happy. Carbon has all 8 electrons. It has this octet. And then, of course, hydrogen only needs a duet. So hydrogen is happy because it's sharing 2 for total. Okay, so if I'm looking at this structure, and let's kind of just draw this in maybe a more simplified way, where we have a bond for every 2 electrons, every 2 shared electrons. You might ask yourself, given this picture, what would the hydrogen-carbon-hydrogen angles be? So what is the angle that exists right there? And I think that you would say, well, it looks like you have a square and it's being bisected, so maybe that angle is 90 degrees. And so if I want to draw a picture of this, I would say, looks something maybe like this. And it's all flat. It's 90 degrees, no problem. That's the molecular shape. However, in reality, methane, CH4, is actually a tetrahedron. So if you were to look at the actual structure of methane, you would see that if you kind of look at the shape that this makes, that it's not flat. It is in fact tetrahedral looking, so a 4-sided structure. And that the hydrogen-carbon-hydrogen bond angle is not in fact 90, as the Lewis structure would kind of give us or make us believe, but it's 109.5 degrees, so it's larger. It's farther apart than the 90 degrees. And this leads us to an important statement, which is that Lewis dot structures are important, and they allow us to create the molecules that are stable, so that everyone has an octet or a duet in the case of hydrogen, and we are able to make molecules using Lewis dot structures, and we can do them accurately. However, even though it gives us the connectivity, it doesn't actually give us the shape or the geometric arrangements. For that, we have to use a different kind of thinking. Luckily for us, the thinking that we're going to use is actually very intuitive. It has a very fancy name. It's VSEPR theory. So VSEPR theory, also known as valence shell electron pair repulsion theory. And this is a fancy way of saying that inside a bond, a covalent bond, there is an electron pair, and negative and negatives repel each other. Same charges repel each other, so these electrons are going to try and be as far apart as possible, and they're going to do this to minimize repulsions from each other. So basically what you're going to do is you are going to look at taking the total number of groups around an atom, so we're talking now about atoms or lone pair electrons, and we'll get to this in just a second, and we're going to try and put them as far apart as possible to give us the shape of the molecule, and that will give us an accurate representation of what this molecule actually is going to look like. Okay, so let's kind of start and let's kind of go through some of the shapes that we can have that we use as chemists to describe molecules. And so if you have a center atom and you have only two other atoms that are being bound to it, okay, and it can be any other atoms. Perhaps an example of this might be carbon dioxide. Okay, to put two atoms as far apart from each other as possible, you're going to put them on opposite sides of the center atom, and that's going to give you 180 degrees between the two attached atoms. And in fact, we're going to describe this as a linear arrangement of the two bound structures to the center atom. Now, if we take this one step further and we add a third object to our center atom, and we want to try and maximize the amount of distance that exists between the three objects, then what we're going to do is we're going to create an arrangement of three objects in plane. They are in plane, so they're all in one plane, and they are 120 degrees from each other. And that's the farthest bond angle you can have, and we're going to call this trigonal for 3, and trigonal planar because it's all in the same plane. So this is a trigonal planar structure. So it's flat, and each one is 120 degrees from each other. Okay, so here we are with a center atom with 4 other atoms around it. So a great example, once again, is we have a CH4, and so we're going to have maybe one of these hydrogens is going to be coming out at us, and one of them is going to be kind of going away from us, and 2 are kind of in the plane of the drawing page. And what we can do is we can kind of say, oh, we're going to get ourselves a tetrahedron looking like structure, and in this case we have maximized the distance that exists between the substituents. So if you had made this flat, they would have been 90 degrees to each other. 109.5 degrees is considerably farther from each other than the 90 degrees, which is a good thing because you're minimizing that electron repulsion. Okay, so as you begin to tack on more and more atoms to a center atom, then you begin to run into the difficulty that you begin to have to put atoms pretty close to each other. You just don't have a choice anymore. So when you get to 5 atoms around a center atom, as in the case of PCl5, shown right here, the farthest you can get away from them is a structure called trigonal bipyramidal, which is fancy sounding, but in fact really what it is that you have 2 pyramids. Right, so you have a pyramid number 1, and then you actually have a second pyramid below, and this is a trigonal. So you have 3 atoms in the center, 3 atoms in the center plane, trigonal, just like the trigonal planar. But now you have trigonal bipyramid, right? So trigonal bipyramid. Okay, and this means you actually have 2 different angles here. You have in the center atom, you have in the plane of the page, you're going to have 90 degrees between the trigonal planar, the equatorial, if you will, equatorial like equator of the Earth substituents to the top one or the bottom one. And then you also are going to have a second angle, which is exactly like it was with the trigonal planar, that these are going to be 120 degrees apart from each other. So you've got both 90 and 120 degrees in the trigonal bipyramidal structure. Okay, lastly, we have octahedral, and this is where you're trying to put 6 atoms around a center atom. And really, when it comes to molecules that we regularly find around us, this is about as cluttered as it gets. It's pretty unusual to go beyond this. It is possible to go to 7, and in fact I think there's even an example of 8 atoms around a center atom. those are really unusual. The last normal one will be having 6, and to space 6 things around each other to maximize the distance, you're going to have an octahedron to do that. And so what this results in is that you have kind of a square equatorial positions, and each of these are going to be 90 degrees from each other. And then you're also going to have 90 degrees existing between any two and the axial versus the equatorial. And this kind of gets us this kind of octahedral looking structure right here. Okay, so here's some examples and the ways in which that we can understand what their shapes are going to be. So what we're going to do here is we're going to actually look at the number of groups being either atoms or lone pairs that are going to be attached to that center atom. And then from that number of groups, we can predict the shape and what the bond angles are going to be. So to give you an example, beryllium dihydride. So we have the beryllium and we have the hydride here. And this is number of groups are going to be 2. What am I saying by groups? Once again, I'm talking about the number of things that are attached to that center atom. And so we would predict in this case that we have a linear arrangement of atoms and that the bond angle should be about 180 degrees. You know, we get to something perhaps like pH5. pH5 is going to have 5 groups attached to it. And to maximize the distance of those 5 groups is going to give us an arrangement where we have both 120 degrees and we have 90 degrees. And this is our trigonal bipyramidal structure. So these are examples that give us the number of groups and the shape and the bond angle. So you'll notice that we refer to these as groups, and we're not talking necessarily about atoms, and that is because you can count a lone pair and an atom as something that will affect the shape. And so you can kind of see here that CH4, CH4 we would predict has 4 groups because there's 4 hydrogens surrounding that carbon, but NH3 also has 4 groups. Why is that? Because for nitrogen to have its octet, it needs to also have a lone pair, right? 2 electrons, 3, 4, 5, 6, 7, 8 from the bonds. H2O also has its complete octet around it, and it has 2 lone pairs, right? So these things are groups, they count, and as a result, that you count them when you're describing the shape. Now, one consequence of having lone pairs instead of atoms is that a lone pair is like a really concentrated form of electron density, and as such, it tends to repel everything around it a little bit more strongly. And so when one compares perhaps methane to ammonia, you can see here that actually the CH4 bond angle has actually contracted a little bit. It's actually gotten squeezed down. And the reason for that is because this is actually pushing down the other hydrogens. It's actually kind of pushing them away from the lone pair. The lone pair is really repelling those bonds. And as a result, it's squeezing the the H and H bond to make it a little bit smaller. The other consequence of having lone pairs is that although they undoubtedly exist, they are reactive, they're necessary for completing an octet. We use them in Lewis dot structures, and we use them to think about the structure here. We actually don't describe them when we're describing the shape. The molecular shape of a molecule, the molecular geometry, is only given by the molecule, the atoms in the molecule. And so, for instance, we can have 2 scenarios here. We can have scenario number 1, where we have a center atom and we have 3 atoms bound to it. And we can see that this is a trigonal planar structure. We can have a very similar geometries, right? These are close to 120 degrees, just like before. They're not exactly like 120 degrees, but they're pretty close. Where we have 1 lone pair and 2 bonds, and so I think that we would intuitively want to call this a trigonal planar structure too, but we don't actually see this as scientists. That we can't see that using our modern instrumentation. So instead, what we do see is we see this. We describe this as being bent. So this gets it's a new name for a similar shape, just simply because we don't see the lone pair. Another set that is going to be commonly seen, here we have our tetrahedron, just like methane. If we were to replace one of the atoms with a lone pair, now we no longer see that lone pair, but we have a very similar looking shape. And so you can kind of see what we see here. We see what looks to be like a kind of like an Egyptian pyramid, and we're going to call this a trigonal pyramidal type structure. And then lastly, things like water right here, water, which if you were to count the lone pairs would be tetrahedral, but since we don't see them, once again is an example of a bent molecule. Okay, so let's do a practice problem to kind of solidify this idea here. And so let's kind of go through it. So we have H3O plus, and so oxygen is going to be right here in our condensed periodic table. It should have 6 valence electrons associated with it, and the hydrogens should each bring along 1, so we should have a total of 9 electrons. Let's see, 9 electrons. And so if we were to kind of put that oxygen right there, and then basically give it an octet, and put the 3 hydrogens with their duets around it, then of course we have to account for formal charge. And so if we look here, oxygen should have 6, and if you have around it you have 1, 2, 3, 4, 5, 6, 7, 8, but we can take half from the bonds. Then we should have 1, 2, 3, 4, 5, so it's 1 too few, so this should give us a plus charge on the oxygen, which is similar to right there. So that's our Lewis structure. We're going to determine the number of groups. So how many groups do we have? Well, we have 3 hydrogens and 1 lone pair, so we should have 4 groups. Okay. We're going to identify the shape from those groups then. So if we look at something with 4 groups, we would think off the top of our head a tetrahedral type shape. That's putting them as far apart as possible. And so let's kind of think about that. So we would have a tetrahedral. But let's be careful about this, because one of the 4 groups is not an atom. And a tetrahedral shape would be 4 groups that are all atoms. So if it's not a tetrahedral, if it's in fact 1 less than that, then we would say it's a trigonal pyramidal shape. Trigonal pyramidal shape. And if you need some review, you can go back a slide and look at some of the shapes that result from having lone pairs in these structures. And this would be the molecular geometry. Okay, let's do a little bit more challenging problem, perhaps. So CH2O. So this is molecule, and it's got carbon in the middle. I'll kind of give you guys that right off the bat. And oxygen and hydrogen and hydrogen. Okay, so this has a total of 6 plus 4 is 10 plus 2 is 12. So we have 12 electrons total. Let's see if we can't do that right here. And so we're going to have 1, 2, 3, 4, 5, 6, and then 7, 8, 9, 10, 11, 12. But it looks like to me that although we gave oxygen as octet, carbon is lacking an octet. So this is not a correct structure. So let's go ahead and erase this one, and we'll try this over again. When you're making Lewis dot structures and you kind of don't come up with the right electron count right off the bat, then the next thing you want to do is think about maybe making a double bond. So let's think about maybe doing something like this. So now if we look here, it looks like this one has all 8 of its electrons. Let's keep adding them in. Let's give oxygen the remaining electrons that it needs, and let's count them up. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So excellent, excellent. This is going to be our structure right here. This is actually formaldehyde. This is what you use to preserve dead animals in for studies. Okay, so we could look at the shape of both carbon and oxygen. Let's look at just the shape of carbon right here, and we're going to determine the number of groups around the atom. And so even though we have 4 bonds, we only have 3 groups around us. So we have 3 groups. And because we have 3 groups, in this case, we want to go back and look at our previous example, and we can see that putting those 3 groups as far away from each other gives us a trigonal planar shape. And we don't have to worry about lone pairs in this case. There are no lone pairs on that particular carbon. And so that is the shape. It is a flat molecule. It's kind of a triangular in shape. Okay, so this is actually an amino acid. This is a picture of an amino acid, and it's actually it's in a conformation that already shows its shape. And so hopefully you guys can kind of see this is how it should look in reality, and we'll kind of show you hopefully maybe how you can kind of see the shapes just given the molecule. So this particular center carbon right here, you can kind of see that this is right here a trigonal planar, right? It has 3 groups around it, so it's trigonal planar around that center carbon. Perhaps we wanted to maybe not talk about that carbon, but maybe talk about this oxygen right here. This oxygen has 2 groups around it, and we can see how it is bent, has a bent shape around it. So don't be confused. This oxygen, of course, has several lone pairs, but once again, we can't really talk about the lone pairs when we're talking about shape, the molecular geometry. We simply just talk about the atoms that are around it. If we were to talk about maybe this nitrogen right here, we could maybe see this one is in a kind of a wonky way, so it's not as easy to see, but we can maybe see this one. It's in a trigonal pyramidal shape. So there's 4 things around it, one of which is this lone pair sitting in the back. We don't count that one, but it kind of gives it this pyramid-looking shape that we can kind of describe. And then lastly, we can talk about this carbon, the center carbon right here. And this one has 4 groups around it, and so it's going to preferably take on a tetrahedron-like shape with the carbon in the middle.